Section 11.3 begins with talking about the estimates of sums. Section 11.3 is the integral test, and it says, in general, it's difficult to find the exact sum of a series. Now, you can accomplish this for geometric series and the series the sum of 1 over n times n plus 1, because in each of those cases, we could find a simple formula for the nth partial sum s sub n. So those were easy to do because geometric has a formula and the other sum was telescopic. But usually it isn't easy to discover such a formula. Therefore, in the next few sections, we develop several tests that enable us to determine whether a series is convergent or divergent without explicitly finding its sum. In some cases, however, the methods will enable us to find a good estimate of the sum, and the first test is improper integrals. Now this is the integral test. It says, suppose f is continuous positive decreasing function over the interval from 1 to infinity, including 1, and let a sub n equal f of n. Then the series from 1 to infinity of a sub n is convergent if and only if. Now that if and only if means it can go both ways. So it's convergent if and only if the proper integral is convergent. That means if the proper integral is convergent, then the series is convergent, and if the series is convergent, then the proper integral is convergent. So that gives us two results. Number one, if the integral from 1 to infinity of f of x is convergent, then the sum from 1 to infinity of a n is convergent. And number two, if the improper integral from 1 to infinity of f of x dx is divergent, then the sum from 1 to infinity of a n is divergent as well. Now, there's a note here. It doesn't always have to start at n equals 1. Notice this summation starts at n equals 4, so our integral starts at 4. Also, it's not necessary that f always be always decreasing. What is important that f is ultimately decreasing? That means it's decreasing from some larger number n, and that's generally when we use that partial summation. So then when the summation is convergent, then the whole sum is convergent by note 4 of section 11.2. So let's summarize that real quick. Let f be a positive, continuous decreasing function. Over the interval from 1 inclusive to infinity, and let a sub n equal f of n. Then the integral from 1 to infinity of f of x is, we have two cases. A, if it's convergent, then the sum from n equals 1 to infinity of a n is convergent. And B, if it's divergent, then the sum from n equals 1 to infinity of a n is divergent. So that's the big key here. This is called the integral test. We probably should have labeled it at the top, but it was on the last page. So here we go, the integral test. Now I like the integral test because I like integration and it seems nice and simple. So let's look at a problem, and it says decide if the series, the sum from n equals 1 to infinity of 1 over n squared plus 1 is convergent or divergent. So we think about this. This graph is continuous. It is positive. It is decreasing over the interval. So we can use the integral test and say the integration from 1 to infinity of 1 over x squared plus 1 dx. Now, in order to do an improper integral, we have to say the limit. Let's say the limit as m approaches infinity. I like m. From 1 to m over x squared plus 1 dx. Now that integration is not bad, but here we have the limit as m approaches infinity. The integration here is inverse tangent, where a equals 1, because that's the square root here. So we have 1 over 1 inverse tangent of x over 1 from 1 to m. Let's clean it up a little bit. The limit as m approaches infinity, the inverse tangent of x from 1 to m. Now, let's plug the bounds in. So we have the inverse tangent of m minus the inverse tangent of 1. Now when we plug in the limit, what we have is we have the inverse tangent of infinity minus the inverse tangent of 1. Now if you think about inverse tangent, I think about the tangent graph when I do this. So here I have pi over 2, and we have negative pi over 2. Those are the bounds. And tangent goes up like this. So as I approach the positive infinity up here, I'm approaching the value of pi over 2. So this equals pi over 2 minus pi over 4. So that would be 2 pi over 4 minus pi over 4 equals pi over 4. So this converges. So we say, since the improper integral converges, then we know that the series converges. Thus, the sum from n equals 1 to infinity of 1 over n squared plus 1 converges. If the improper integral converges, then the series converges. If the improper integral is divergent, or if it diverges, then the same is true of the series. So let's look at an important one. It says the sum from n equals 1 to infinity, 1 over n to the p. And we have several cases here. So let's start off with case number 1. Let's let p equal 1. So we have the sum from n equals 1 to infinity of 1 over n. Now we need to think about what that means. That means 1 plus 1/2 plus 1/3. That's the harmonic series that we did in the last. So the series 1 over n, the series is positive, the series decreasing, the series is continuous. So let's look at the improper integral from 1 to infinity of 1 over x dx. Now we need to look at the limit because it's an improper integral. So I'm going to do the limit from 1 to m. The limit as m approaches infinity from 1 to m. Now when we integrate that, the integration of 1 over x is natural log of x. So we have natural log of x from 1 to m. So we have the limit as m approaches infinity. So this means we have the natural log of m minus the natural log of 1. By the way, the natural log of 1 is 0. The natural log of infinity is infinity, so this is divergent. So that means that this one is divergent. Let's look at the next case. For case 2i, let's let 0 be less than p, which is less than 1. So this means that p is a fraction because we have a root here. So we're going to say the sum from n equals 1 to infinity, 1 over n to the p. So we have the integration from 1 to infinity, 1 over x to the p dx. Now p here is a constant, it's a number. So we're going to do the limit as m approaches infinity, 1 over m, and here we have 1 over x to the p. Let's write that as x to the minus p because it's easier to integrate that. X to the minus p dx. Now remember, x is my variable here. X is our variable. So we say the limit as m approaches infinity. We add 1 to that, so we say negative p plus 1. And then we divide by the new power of, can we call it 1 minus p? And we're going from 1 to m. Now remember, x is our variable here. So then I'm going to switch colors on purpose. So we have the limit as m approaches infinity. And when we plug in m, we have 1 minus 1 over p, x to the, that's not x, that's m. That's the hard part. That's where our variable is, m to the 1 minus p. We just switch those letters. Minus 1 over 1 minus p times 1 to any power is 1. So what we need to look at here is this part right here. So we have 1 minus p as our power of m. Now remember that p is between 0 and 1, so it's a fraction. It's a small value. So what we have here is we have infinity to a positive power, so this leads infinity, and then minus 1 over p, 1 minus p, which is still infinity. So this is divergent, so that means case 2 is divergent. So case 3, we're going to pick, we're going to let p be less than 0. So that means p is a negative value. Now what that means is when I look at this summation, I have 1 over n to the p, but p is a negative value. So let's call it the sum from n equals 1 to infinity of n to the q. Because p is negative, that means if I take the absolute, let's let q equal the absolute value of p. Because my negative exponent would move to the top up here. And then you can see that as we approach infinity, that is infinity. We could just use a limit to say the limit as n approaches infinity of n to the q equals infinity. So this one is divergent. The other way to do that is to, we could go back to this integral and do it there. But let's not. Case 4, let's let p equal 0. So we have the sum from n equals 1 to infinity of 1 over n to the 0 power, which means the sum from n equals 1 to infinity of 1. And when you add 1 an infinite number of times, you get divergent. So we could say the limit as n approaches infinity of 1 equals 1, which is not equal to 0. Therefore, it's divergent because we're looking at the sum of a series. So we have divergent on this one as well. So now let's look at case 5. Let p be greater than 1. So we have equal 1, between 0 and 1, at 0, less than 0. So now we need to go greater than 1. So we're going to say the sum from n equals 1 to infinity of 1 over n to the p. This is a positive decreasing continuous function. So we can say, look at the integration from 1 to infinity of 1 over n to the p. Let's not call it n. Let's call it x to the p dx. Now you can see that's exactly what we have over here. Our conditions for p are different. So that means we have the limit as m approaches infinity, 1 to m, x to the minus p dx. So when we integrate that, we have the limit as m approaches infinity. We have 1 over negative p plus 1 times x to the negative p plus 1 from 1 to m. So we have the limit. It's a little nicer to write it the other way, and it's a little helpful. We have 1 over 1 minus p, x to the 1 minus p from 1 to m. Now let's plug in the m's. So we have the limit as m approaches infinity, 1 over 1 minus p, m to the 1 minus p, minus 1 over 1 minus p. All of this is in the limit. And 1 to any power is 1. So now let's go back to the same value here. Now remember, p is defined to be greater than 1. So if we come here, p is greater than 1, that makes that negative. That means we technically have the m in the denominator, and 1 over infinity goes to 0. So here we have the limit gives us negative 1 over 1 minus p. We don't technically need that parentheses. Times 1 is just that. So this integral converges, and since it converges, then since the improper integral converges, then this one converges. So what we looked at here is called a p-series, and it's very important. So let's make a note here. This is p-series. And it says the p-series, the sum from n equals 1 to infinity of 1 over n to the p. It's not n times p. It needs to really look like it's n over p. Is number A. We'll go with A. It's convergent if p is greater than 1, and it's divergent if p is less than or equal to 1. Now we're going to use that a lot, so keep it in mind. That's something you should take note of, make a big note of, write it down. It's something you need to know because we're going to reference it often. We're going to say p-series and run with it. So look at this example. This example says the series n equals 1 to 3, 1 to infinity, 1 over n to the third. Now look at your power of n. Your power of n is 3, which is greater than 1. Since it's greater than 1, we say this is convergent. Convergent because it's a p-series. You don't have to say because, you can just say p-series. P-series convergent. So the next example, it says the example, that's an example. It says the sum from n equals 1 to infinity of 1 over n to the 1/3. And when you look at this one, the power of the integral of n is a fraction. It's less than 1, and it follows the format. So we say p-series, and then we can just say divergent. Diverges, divergent. Outside of that, we would use the improper integrals for the improper integral test. So the next problem says determine if the series, the sum equals n equals 1 to infinity, ln of n over n converges or diverges. So you have to kind of look at the graph, look at it on your calculator and come back. But it is definitely a decreasing, positive, and continuous function. So we can use the integral test, the integral from 1 to infinity, natural log of n, that should be natural log of x, over x dx. So the first thing we need to do is deal with the improper integral, the limit from n to infinity, 1 to m, ln of x over x dx. Now, when you see natural log, you have one of two choices. Your first one is u sub because it's easier. Your second one is integration by parts. So let's use u sub. Let's let u equal natural log of x, and then du is 1 over x dx. Oh, that works out nicely. Can't you just see that 1 over x dx happening? If not, dx equals x times du. So then we have the limit as m approaches infinity, the integration from 1 to infinity, and we're not using infinity, the integration from 1 to m. Now the natural log of x is u, and then we have that over x times. Now what's really good is that my dx is x du. So these x's cancel nicely. If your x's don't cancel out, you can't integrate the combination of u's and x's. Something's wrong. So we have 1 over m u du. So we have the limit as m approaches infinity. Now the integration of u is 1/2 u squared from 1 to m. So we have the limit as m approaches infinity. 1/2, and remember u is natural log of x, quantity squared from 1 to m. So we have the limit as m approaches infinity. I have 1/2 natural log of m, quantity squared, minus 1/2 natural log of 1, quantity squared. By the way, the natural log of 1 is 0, so that's gone. Now the natural log of infinity is infinity. Squared is infinity, times 1/2 is still infinity. So this diverges. Therefore, you can always use 3 dots to say therefore. That's what our abbreviation in math. Therefore, the sum from n equals 1 to infinity of natural log of n over n diverges as well, or is divergent. There are several more I'd like to look at. They also talk about estimating the sum of a series, but I'm going to focus for now on convergent and divergent. There's several I'd like to look at. Let's talk about number 4. It says the sum from n equals 1. This is number 4 in your textbook. From n equals 1 to infinity of n to the minus 0.3. Now, this is a p-series, so let's look at it from n equals 1 to infinity, and I have 1 over n to the 0.3. Do you see that 0.3 happening there? So I definitely have the p-series format. Here's the problem. Is p larger than 1 or less than 1? But I have a p-series here. So p is less than 1, so this is divergent. Those are nice and easy. There's several of those in the work, so that's not bad. Let's look at number 14. Number 14 is not bad. Just something you need to see. It says 1 plus 1 over 2 square root of 2 plus 1 over 3 square root of 3 plus 1 over 4 square root of 4 plus... Now, that's not too hard to see the pattern. We know that this is the sum from n equals 1 to infinity. It's the series. And we can call it 1 over n square root of n. But let's make it even easier. Notice that this means the sum of 1 over n times n to the 1/2, right? Now what do you do when you have like bases? You multiply those powers. So we have 1 over n to the 3/2. Look at that p-series right there. P-series, yay! In the p-series, you just have to pay attention to where we are. And this value of p is greater than 1, so we have convergent. Convergent or converges. I'm okay either way. The problem says determine if it's convergent or divergent, so we tend to write convergent. I don't know why we don't have an abbreviation for it, but we don't. Number 12 is a little bit harder. It says 1 over 5 plus 1 over 7 plus 1 over 9 plus 1 over 11 plus 1 over 13 plus ... We have to figure out the pattern and be able to do it. So I need to look at them. So I have 1/5. A sub 2 is 1/7 because I'm looking for a connection between n and what we have here. So think about the fact that we're adding 2 to every denominator. So remember that addition means repeated multiplication. So when I add out 2 every time, that means I've got a 2n involved. So if I go back to the number 1, if I multiply 2 times 1, I get 2, and then I need to add 3 to get to 5. And then here, 2 times 2 is 4, and if I add 3, I get to 7. And 2 times 3 is 6, plus 3 is 9, so it looks like this is what my term is, that this is an. So check a couple more. It appears to be right. So we can say that this is the sum from n equals 1 to infinity of 1 over 2n plus 3. So now we can, it is definitely positive, decreasing, continuous. So let's look at the integral from 1 to infinity of 1 over 2n plus 3. That's not supposed to be n, that's supposed to be x. Dx. So let's look then at the integral. We have an improper integral, as we do on all of these. Sorry for stating the obvious. We have the limit as m approaches infinity of 1 to m of 1 over 2x plus 3 dx. You see u sub. Let's let u equal 2x plus 3. Then du equals 2 dx. So dx is 1/2 du. So now we have the limit as m approaches infinity. My limits get a little sloppy. If yours get a little sloppy, that will be okay. So we have the limit from 1 to m of 1 over u times 1/2 du. So what's the, let me set it all up. So when we integrate 1 over u, we don't need the integration symbol anymore. When we integrate 1 over u, we get natural log of u. Natural log absolute value of u, but n's are positive, so it's okay. So we have 1/2 from here. We have 1/2 natural log of u from 1 to m. Don't forget to put u back in. So we have m to infinity. 1/2 natural log, what is u again? 2x plus 3 from 1 to m. So then we have the limit as m approaches infinity. 1/2 natural log of 2m plus 3 minus 1/2 natural log of 2 times 1 is 2 plus 3 is 5. So we have the limit. This last part of the term is a constant, so let's talk about here. 2 times infinity is infinity, plus 3 is still infinity. And the natural log of infinity is infinity, and half of that is still infinity. So we have infinity, and then we're subtracting something. So this means it's divergent. So since it's divergent, we can say, therefore, the sum from n equals 1 to infinity of 2n plus 3 is divergent. You could go back to the way the problem was written, and we can say, therefore, where do we start? 1/5, right? 1/5 plus 1/7 plus 1/9 plus 1/11 is divergent. You may write your answer either way. But you don't just end up with divergent on your series and then just say divergent. Now, the next video is optional because we have covered all that you need in order to be able to do the problems. There's probably one more we would do. Let me look at it real quick. But I would hit the next video because I'm going to walk you through a couple more examples. This says, the directions say explain why the integral test cannot be used to determine if it's convergent or divergent. Now here's your hint. That means either it's not positive, or it's not decreasing, or it's not continuous. So graph it on your calculator. Just look at what that y equals looks like and then come back. Okay, so if you look at this graph is definitely alternating. It goes back and forth between positive and negative. And so it is not decreasing, so you cannot use the integral test. So we would say decreasing, not decreasing, not decreasing. So you can't use the integral test. Good news, we're going to talk about what to do with that later. Watch the next video. I'm going to help you with a few more of these problems, and then we'll pick up in 11.4. That's okay. Watch the next video. Thanks. Have a good day.